Okay, so last class we were looking at the distinction area in arc, right? So we saw three regions. Okay, so what are the three regions we saw in arc? Okay, so suppose if you have an arc, okay, so you form a beautiful. So I'm not a good artist, so but still you can imagine. So suppose if this is our anode and this is cathode. So we see just below the anode tip we have anode fall zone, right, and then just above the cathode regions we have cathode fall zone, right, isn't it? And we looked at the distinctive characteristic of these zones. So we looked at in anode fall zone, and because of the positive polarity, it attracts electrons. So electrons accumulate at the tip of the anode and form anode fall zone, and due to that we have accumulation of electrons leading to improper collisions. The collision is not complete. Okay, so the mutual energy exchange is not complete. Therefore, the electron temperatures are much higher at the anode fall zone than elsewhere. Okay, because there is not enough energy exchange, because the number density of electrons are much higher than the ions. Okay, so that also leads to a voltage gradient, right? Okay, so voltage gradient in anode fall zone. Similarly, a voltage gradient in cathode fall zone because of the accumulation of electrons at the surface of the cathode, and which we call it cathode fall zone. Okay, again in cathode fall zone the gas temperatures are much higher, or gas ions temperature are much higher than the electron temperature, because again there is not enough energy exchange between the electrons and ions, right? And because of that the gas temperature is always higher than the electron temperature, much higher, right? And we looked at the functions of cathode. So the main function of cathode to emit electrons, right? So we looked at the cathode functions. So in subsequently we will see the detail about the emissions, but we have seen the cathode emissions like thermionic process, thermionic emission, right? And we looked at the equation which governs the thermionic emissions, right? The electron density is, without referring your notebook, can anyone tell? T square e power minus work function, yes, by, yeah, again Boltzmann. Okay, so the work function we defined as work we do to emit an electron from a material, in this case for example cathode, right? So E is nothing but the charge, and then phi is, it's like an electron volt, sorry. So electron volt is again, so what is 1 electron volt? How many joules is 1 electron volt? Or 1 joule is how many electron volts? First lesson. Okay. So 1 joule is how many electron volts? So when do you say 1 joule? When 1 coulomb of electrons travel over 1 volt, right? When then the energy gain. So obviously 1 joule is 6.242 times 10 power 18 electron volt. Okay, that is 1 coulomb, right? Number density, number of electrons in 1 coulomb, isn't it? So it's all related. So if you say 1 joule is 6.242 times 10 power 18 electron volts, because that is what 1 coulomb we define, right? Number of electrons in 1 coulomb. Okay, if you say 1 electron volt, obviously, if you say 1 joule, it is obviously 6.24 into 10 power 18 electron volt, right? So that's what the work function is, defines the energy, joules, in terms of joules, right? Okay, so that's the joule you need to give for creating an 1 coulomb of charge traveling through 1 joule of energy. It's all simple related. So the work function E phi defines the energy. So work function is again is a material parameter. So for some material it can be very high, for some material it can be low, and we have to have a compromise between the melting point or the thermal stability of the cathode with respect to work function. Because in order to emit the thermionic emission in electrons by thermionic emission, you need to heat it up to high temperature, because T determines the emission, right. So, we dope it with some oxides of a high melting point material, or material which has high thermal stability, so that now we can emit the electrons at a lower temperature or reasonably lower temperature by doping these materials with oxides, because oxides are generally, they have very low work function. And then we looked at the field emission, because not always it is possible to emit electrons by thermionic emission, because sometimes we use, say, consumable cathode. So, in that case, so we need to emit electrons by some other way. So, we use field emissions, high frequency. So, it has to be done with a very high electric energy. So, we go up to 10 power 10 amperes per square meter to emit the electrons by field emission, right. It's clear. So, we looked at the emission mechanisms between the thermionic emission and the field emissions, and we will see in subsequent chapters how these emissions are used to ignite an arc. Okay, arc ignition is done by these two emissions. Okay, so we will see when you want to ignite an arc, how we can promote these two processes. That will come in subsequent chapters when you look at the process itself. So, now before even going to that, we have to study about the third region in this figure, so which is arc column. So, arc column, right. So, we just touched upon the arc column. So, the arc column is electrically neutral, okay, in general. So, therefore, the voltage gradient is not steeper as compared to the anode or cathode fault zone. So, why do you say the electrically neutral? Because the number density of the electrons and ions is more or less equal. Okay. So, when the arc column becomes electrically neutral, we call that state as plasma. Okay. So, plasma is defined as a neutral state of matter. Okay. So, the arc, when it becomes electrically neutral, then it becomes plasma, but then the number density must be equal. So, we need to create as much electrons and ions in such a way that we maintain electrical neutrality. But it is very difficult to attain that state in a welding case. So, we will have to do some modification to the arc itself to make arc into plasma. So, most of the arc welding processes, the arc is electrically negative, because it contains more electrons than ions, right. But in a way you can assume that, you know, in a typical in arc column, of all the arc welding processes, the kinetic energies of these the charge carriers, the electrons and ions, are the same, because there is a mutual collision. The number density is close to equal, maybe slight negativity, but you can say that the amount of the density of electrons and ions are so high. Okay, so there will be a mutual collision between them, leading to an exchange of complete exchange of energy between the electrons and ions. So, therefore, if you look at the kinetic energy of these space carriers, the charge carriers, it is equal. So, if you say that, you know, so we were looking at see one electron, okay, it must be equal to, say for example, ion as well anywhere. So, must be equal to a kinetic energy of a particle as a function of temperature can be determined by 3/2 Boltzmann again, right, it is clear. So, now we will go in even deeper. So, when you say that it has an equal energy, that means that there is a mutual collision. Okay. So, the mutual collision ensures that the complete energy exchange, like in a snooker ball. Okay. So, that means that, so when the electron heats an ion, the electron stops if there is a complete exchange of energy. Okay. And then ion is carrying the energy of electrons and travels further. So, that is the complete mutual collision and exchange of energy. Okay. But it is not always the case, right. So, because the electrons carry very low mass compared to ion. So, ion is nothing but as a gas atom. okay, where it has 1 or 2 electrons lesser than the complete shell it used to have. So, the mass of ion is much higher than the electrons. Okay. So, ideally technically if an electrical neutrality is maintained, if a mutual collision happens, then the electron temperature must be equal to gas temperature, is not it, right. So, that is complete energy exchange system. It is an equilibrium, it is an electrically neutral and thermal equilibrium. System is in under thermal equilibrium as well. Okay. So, this is the ideal state we can have. So, when you define, when you say this plasma, that means that all the subatomic particles, these charge carriers should have a same temperature, and the number density should be such a way that you maintain electrical neutrality. So, that is the state of plasma, right. So, that means that it is like in any other matter, right. So, it does not have any electrical charge, net electrical charge, and all the entities, microscopic entities have same temperature. So, that is plasma. But in our case, because again the electrons are slightly higher in number density, okay, and the drift velocity of electrons are much higher than the ions. What is drift velocity? For example, after the collision, in between 2 collisions, because of the low mass, they can travel much further than the ions, is not it? Yes, the electrons carry low mass compared to ions. So, the average drift velocity between 2 collisions will be much higher for electrons, right. So, if the electron drift velocity is higher, obviously it is also exposed in the system for higher time, more time, is not it. So, they can travel far between 2 collisions because of the high drift velocity given by the low mass. Therefore, the electrons can heat up slightly more, right. So, the electron temperature is slightly always higher than the ion temperature in the system at atmospheric pressure. Okay. So, if you look at the curves at 1 atmosphere pressure, it is more or less equal. You look at the sign I drew, okay. I was so careful not to make any mistake because it is not equal, it is more or less equal. Okay. So, the electron temperature is more or less equal to gas temperature. At 1 atmosphere pressure, it is the case. Okay. So, you can assume, so between 18,000 Kelvin to 18,500 Kelvin, you would say it is equal, right, is not it. We once you want to distinguish 500 Kelvin when the temperature is already close to 20,000 Kelvin. So, that is the case. At atmospheric pressure, the electron temperature is slightly higher than ion and gas temperatures. But when the pressure is changed, when the system is under different pressures, then the situation is not going to hold, because then your drift velocity will change. If you change the pressure, your drift velocity will change. Suppose if you are going to low pressure, so obviously the effect of pressure on the mass is so high, electrons would drift even much faster at low pressure situation, then the electron temperature will increase even further compared to ions, right. It is clear. So, at atmospheric pressure more or less equal, you can say, but when the pressure is increased or pressure is decreased, then drift velocity will also change dramatically. Okay. So, if you are doing welding at 1 atmosphere, you can assume that TE, the temperature of the electrons, are more or less equal to the gas electrons. And these are important. Why these concepts are important? Because I am going to teach you when you look at the heat generation. So, then you need to understand all these phenomena when you are looking at deriving the equation for electrical conductivity of an arc, which is needed because conductivity determines your heat generation, resistivity 1 by conductivity, reciprocal of conductivity, is not it. So, when you are deriving equations for that, you need to understand these concepts. Okay. Okay. So, we will move on for this class. The arc column, again to recall, they consist of neutral as well as charged particles. Okay. Obviously, the electrons and ions will move to respective the electrodes or respective the polarity to either to an anode or cathode based on their charges. Electrons travel towards anodes, ions will travel towards cathode. And because of the number density, equal number of positive and negative charge carriers, you maintain electric neutrality. Once you achieve that electric neutrality, you can claim that you created a plasma, right? And because of the mutual collisions between the electrons and ions, it ensures the local thermal equilibrium. Okay, so the temperature of electrons and gas temperature are more or less equal. And if you achieve such state, it is a clear equilibrium state of plasma, where your plasma reached the electrically neutral and the thermal equilibrium system. Okay. In that system, the kinetic energy of all the particles are the same, which is equal to 3/2 kT. Is clear? Good. But it is not always the case, right? So you have, because of the difference in mass, the electrons drift more, or they travel more. Because of the mass, the drift velocity is also higher, leading to the electrons are heated slightly more than the gas in the system. So at 1 atmosphere pressure, the electron temperature are slightly higher than the gas temperature. Okay, so at atmosphere, what is atmospheric pressure in the Newton per square meter? If you change the pressure of the system, what happens? The drift velocity of the electrons also change. Okay, so obviously at lower pressures, if you look at it, the electron drift velocity will be much higher at low pressures. Obviously, the difference will increase, because the gas, because of the mass, the effect of pressures will be significant when the mass is changed. For example, lighter mass materials would have higher velocities at low pressures than the heavier mass, and that can lead to the change in drift velocity at lower pressures. And because of that, so you will have the electrons gaining more temperature than the gas ions. So the difference will be significant at lower pressures. Yes, it's clear? Any questions? Okay, so we will move on further in the arc column. What happens in the arc column? Okay, so this is what I explained. So at bottom atmosphere pressure, temperature is more or less equal, but always the electron temperature, you should be careful, is slightly higher than the gas temperatures, because electrons are lighter and they have a longer free path because of the high drift velocity, so that they can spend more time and before the energy exchange, which is the collision. Okay, so that they are heated up higher, right? It's clear? So when you say that there is an energy created in the system by the collisions of the ions and electrons, so obviously that energy has to be consumed, isn't it? So suppose if you want to calculate how much energy is generated, we can calculate that by looking at how this energy is spent. Okay, so if you know how you spend that energy, then we know that how much energy is already there before begin with. Okay, suppose if you spend all your pocket money in a day, if you know that how much money you spend, if you sum it up, and you get it how much money you had to begin with, right? So same thing. So when you want to calculate how much energy is generated in an arc, we can calculate it by knowing how much energy is transferred to the system. So when you have an energy is there, obviously the energy is transferred in this case by 3 ways, right? By conduction, convection and radiation, right? So that's how the energy is spent. So by looking at how the heat is conducted from the arc and how it is actually transferred by convection radiation, and we can also know how much energy is created in the system, but it's not that straightforward. Okay, so this experiment we carried out to look at how much temperature is, what would be the temperature distribution of an arc. So this is the real experimental data. So it is done using 200 amperes current of a tungsten thoriated electrode, okay, in argon atmosphere. And this anode is a copper plate which is water cooled copper plate. So it's fully cooled. So when you look at the temperature distribution typical at one atmosphere, okay, so again, so at the center of the arc, the temperature can go up to 18,000 Kelvin. Someone asked a question in last class. Suppose if you are having a metal electrode here, is cathode here is in tungsten, and system is exposed to a temperature of 18,000 Kelvin, won't it melt? It won't, right? You see in real life in gas tungsten arc welding, the electrode tip is stable, right? Why it's not molten? Yeah, it's obviously a melting point. Okay. So the temperature, you see that in the center here, it can go up to 18,000 Kelvin. But still you have the tip not molten, right? Because of the formation of the cathode fault zone. So when you say that the arc column, it starts from, in this case, cathode fault zone. Cathode fault zone is very tiny area, 10 power minus 8, 10 power minus 7. That is what you are exposing. Okay, and this tungsten is conducting heat very effectively, as well as the exposure is towards very tiny area. Okay, and similarly, when you are doing non-consumable electrode welding, you make sure that electrons are moved away. That means that electrons carry heat, more heat than ions. Okay, so the heat is carried away by electrons very effectively from the tip, which is very tiny, already 10 power minus 8. So you don't melt because of the effective conduction, as well as the electrons are not reaching the electrodes. The heat is effectively transferred by the electrons, okay, towards anode in this case. So anode is molten, right, because the electrons are reaching the anodes, which carry the heat. Right, it's clear? Okay, now if you look at the temperature distribution, obviously at the center of the arc column, the temperature can go up to 18,000 Kelvin. The arc envelope, what we call it, is the outer periphery, is known as arc envelope, okay, and it can go up to 10,000 Kelvin. So the temperature of the arc is entirely determined by the nature of the gas, what you have, which is forming the arc. Why is that? Because the gas determines the ionization. Okay. So if you want to understand what is happening inside the arc and how we generate these temperatures, then we need to understand the first basic principle of the generation of the charge carriers. Of course, the thermionic emission, the field emission, they just ignite the arc. Okay, so they supply enough electrons to the system so that these electrons which are generated from the cathode can trigger now the subsequent sustained discharge, which is ionization. Yes, it's clear? So before going to look at the heat balance, first we need to understand how these charge carriers are created. Right? It's clear? Because that is going to determine the temperature distribution. The temperature is arising from the collisions, the heat which is generated in the arc. Yes? Okay. So first we will let understand the basic principle, basic fundamental process that is happening, which is ionization. Right? So when you say the ionization, so what is ionization? We need to define again, right? Okay, so this is simple. When you say ionization, it is nothing but it's a process of removing one electron, okay, from an atom. And in this process, you generate an electron, right, and the atom becomes a positive ion, right. So that doesn't happen by itself. Okay, you need to always supply an energy to an atom so that you knock out an electron. Same as thermionic emission. Thermionic emission, you have work function, whereas in here you have ionization energy. right? You supply an energy which is an ionization energy because you are creating an ion, okay, so that you knock out an electron from an atom. Okay. So, this is the very basic reaction helps in sustaining the discharge. So, you pump up electrons by thermionic emissions. Okay. So, those electrons subsequently, once they attain the energy equal to the ionization energy, then obviously that electron can trigger the ionization in subsequent reactions. Okay. So, once the electrons which is emitted by thermionic emission, they attain the energy equal to ionization energy, then they subsequently knock out subsequent electrons from the shell of the gas atom. Okay. So, this reaction is endothermic or exothermic? Endothermic, because you supply energy, right. So, this energy is consumed by the atom to release an electron. Yes, it's clear. So, the EI again, it is a function of the material, in this case a function of gas, because EI can be changed if you change the composition of the gas or nature of the gas, right. It's clear. So, the degree of ionization, suppose if you want to calculate how much amount of ion you generate at a given temperature, you can use this equation. It is a very famous equation. An arc is a beautiful star. Okay. So, if you know that what gas you are using it, and you know the ionization energy, right, and you get the spectrum, and spectrum is not constant, it changes, okay, from the middle of the arc column to the envelope. If you accurately predict the spectrum, you can calculate the temperature, isn't it, right? It's clear. So, for yeah, what is the P? What could be P here? It is pressure. Okay. So, whatever your pressure, P goes away, right. So, if you change the P, the pressure, obviously you also change the fraction ionized. Okay. So, it is negligible at 1 atmosphere pressure, but it is not the case, right. In arc we can neglect P. Arc pressure is based on the curve I showed you already. Okay. So, if you keep the pressure constant, the only thing is going to affect your ionization fraction. So, again alpha is the fraction ionized or degree of ionization. This is nothing but the degree of ionization over the unionized gas atoms. That is a fraction. Okay. So, total or the unionized with the ionized fraction is, again this is constant, and EI is the ionization energy, right. So, your pressure is constant, the only thing which is dependent on is the temperature, or in other word, if a gas has high ionization energy, then the temperature should be increased in order to ionize. Okay. It's clear. So, if you look at the function of the ionization energy as a fraction ionized, obviously if you have a very high ionization energy, you need to increase the temperature to much higher, then only you can create ions. Saga equation. Saga equation defines the shape of this curve. Okay, it is exponential decay. Okay, so that is what the exponent here is doing, a negative sign here. Okay, so the equation determines the shape of this curve, right. It's clear. If you look at thermionic emission, is similar equation, isn't it? AT square e power minus work function divided by kT. That is also you are emitting an electron. Here also you are emitting an electron. There it is work function. Here is ionization energy. Okay, the nature of the curve, this is exponential decay. This is similar as a function of temperature, isn't it? Yeah. So, this curve when you fit it, you will get Saga equation. Okay, so this curve if you fit, so you will get a Saga equation. And what does the curve say? For example, if you have very high energy, the ionization energy, if you want to create, say for example, half of the gas atoms should be ionized, 50% ionization. In this case, so you need to increase somewhere about 11,000 Kelvin. The gas temperature should be increased 11,000 Kelvin if your ionization energy is somewhere 9 electron volt. Okay. So, if a gas has a very low ionization energy, obviously you can ionize the half of the gas atoms at much lower temperature, 6,000 Kelvin. Okay. In other words, if you say that the heat is emitted in terms of heat generation, okay, that means that suppose if you are giving an energy to the system, so obviously when the gas has a very low ionization energy, you also create low temperatures, isn't it? Whereas if you ionize the gases with high ionization energy, you also create more heat, more temperatures, isn't it? It is the same, you are telling differently, right? So, gases with low ionization energy can ionize at very low temperatures. Okay. In other words, if a gases with low ionization energy, when they get ionized, the temperature of the system is also low, isn't it? So, when you use for example, helium as a shielding gas, helium has the highest ionization energy. Okay. So, when you use helium as a shielding gas, when you ionize helium, obviously the system temperature should also be very high. Obviously, arc temperature will also be very high, right? Suppose if you are ionizing in a vapor, metal vapor, okay, and metal vapor has generally very low ionization energy. So, then the arc temperature would also decrease, or it will be very low compared to when you have a system where you have a helium or argon for that matter. Yes, it's clear? Good. And this curve is clear, right? So, this is nothing but the Saga equation.